calculator for, but a calculator that can handle it will make your life much, much easier. Let me double check on this. That looks okay. All right. So last time we talked about the fundamental principle, and we're going to go from that today into permutations. So we have quite a bit to cover in permutations. It's a lot more than 11.1. 11.1 is a really short section, and this is a much more in-depth section. So we'll get through this and probably 11.3 today. I think that should, or at least part of 11.3. So there's 4 things we're going to do in 11.2. We're going to use the fundamental accounting principle to count permutations. We're going to evaluate factorial expressions. We're going to use the permutations formula, or if your calculator can do it without using the formula, you may use your calculator for it. And we'll find the number of permutations of duplicate items. Of these, the first 3 are the most important for you to be able to do. The last one is good. It might show up as a question, but it'll be like just one question as opposed to a bunch of questions, or approximately. So we're going to have some vocabulary here. A permutation is an ordered arrangement of items. This happens if you don't use any item more than once. You can't double count anything. And the order of arrangement makes a difference. I used to teach elementary school. One of the things I sometimes like to do to think about a permutation is lining elementary school kids up into a line, like you're taking them to lunch or something. You might think back to your own time in elementary school and think about if you wanted to be at the line leader or not, or if you wanted to be at the end of the line or not, or if you wanted to stand by whoever was your best friend that particular day or not. Order matters. It matters if Jeff is first in line or if Teresa is first in line. Those are 2 different lines. It matters if Alicia is next to Patricia or if Alicia is next to Leroy. It makes a difference. Order of arrangement makes a difference in a permutation. If the order matters, if it matters who comes first, second, or third, think about runners in a race. It typically matters who comes in first, second, and third. So that would be an example of a permutation if order matters. It matters what we put first, what we put second, what we put third. Sometimes order won't matter. We'll talk about those things in the next section. But for a permutation, order matters. What comes in first, second, third, fourth, fifth, etc. For example, here we're going to use the multiplication or the fundamental counting principle that we talked about last class. You have 7 favorite books and you are going to put them on a bookshelf. How many different ways could you arrange those books, assuming that the order matters to you? And so to think about this as a counting problem, let's draw the places for the books. Here's book 1, book 2, book 3, book 4, book 5, book 6, and book 7. So I have 7 slots on my shelf to put these books on. For my first slot, I have a total of 7 possibilities, right? I have 7 books. I could put any of those books on that first slot. For my second slot, I don't have 7 possibilities anymore. I only have 6. I only have 6 because I've already shelved one of the books, so I only have 6 books left. That means for each spot on my bookshelf, I have 1 fewer choice, 1 less choice, I should say, than I did for the slot before. So I have 7 possibilities to put on the first slot on the bookshelf. I've used the possibilities. I only have 6 now for the second. I only have 5 for the third, 4 for the fourth, 3 for the fifth, 2 for the sixth, and 1 for the seventh. Each time I shelve a book, I lose a possibility because I've shelved that book. I don't have it to choose from anymore. I can't shelve a book more than once. And so, using the multiplication or the fundamental counting principle, which is also called the multiplication counting principle, we can just multiply these choices together. I have 7 choices for spot 1, 6 choices for spot 2, 5 for spot 3, and so on. So that's going to be 7 times 6 times 5 times 4 times 3 times 2 times 1. I have a total of 5,040 choices, or 5,040 ways. All of the problems that you are going to do in this section, or almost all of them, all of the word problems, will require a label of some sort. So 5,040 ways. How many different ways? 5,040 ways. This is not something you could reasonably find just by making a table, right? You couldn't make a tree diagram to show this. I mean, you could, but it would take lots of paper and lots of time. That's where the multiplication, or the fundamental counting principle comes in really handy. That product, 7 times 6 times 5 times 4 times 3 times 2 times 1, has a special name. It's called 7 factorial. Now, when I was taught to say this word as factorial, and some people say factorial, and I kind of, sometimes I split the difference, and sometimes I say it one way or the other. I do not say it consistently because I've heard it too many different ways. Doesn't matter how you say it, as long as you can work with it. It is written with an exclamation point. When you see a number followed by an exclamation point, it means start with that number and multiply it by each number smaller than it, each integer smaller than it, down to and including 1. So 5 factorial, for example, is 5 times 4 times 3 times 2 times 1. 10 factorial, I'm not going to write all of these out, but 10 factorial would start with 10 times 9 times 8, and it would keep going, times 7 times 6 times 5 times 4 times 3 times 2 times 1. 20 factorial is 20 times 19 times 18 times 17 times 16, and so on. 1,000 factorial, which you will never work with, is 1,000 times 999 times 998 times 997 times 996, and you're going to get numbers so large that your calculator can't handle it. In fact, your calculator can't usually handle numbers bigger than like 50 factorial or so. They get really large very quickly. You can only find a factorial if it is a non-negative integer. 2.5 factorial doesn't make any sense. -3 factorial doesn't make any sense. It's always going to be non-negative and an integer, never a fraction, never a decimal. By definition, mathematicians say that 0 factorial equals 1. There are logical reasons for this. If you Google, or not Google, if you go onto YouTube or some other video site and look for a video called, just type in 0 exclamation point, you will find tons of videos of people explaining why 0 factorial is 1 instead of 0. I suppose you could think maybe logically, if we don't make any choice, that's the same as making a choice, maybe. It's really defined as 1 just so the formulas we work with work out. That's the big reason why. Otherwise, we get into trouble for some of the things. So be aware that 0 factorial is 1. Be aware that for others, for any positive integer, that number followed by an exclamation point is the number times each smaller integer down to and including 1. So 4 factorial is 4 times 3 times 2 times 1, which is 24. 3 factorial is 3 times 2 times 1, which is 6. And so on. Your calculator should have a factorial key on it. If you have a scientific calculator like you need for the class, there is probably a factorial key or a factorial menu option somewhere on your calculator. If you are unsure, if you can't find it, take a clear picture of your calculator's keypad after class that includes what the calculator's name is, like what its model number is, and email it to me, and I will see if I can help you find it. I can't guarantee I will be able to help you find it, but I will try, because that's the same thing that would happen if we were in person. If we were in person after class, I would say, bring your calculator to me and we'll see if we can find it. Normally, everyone is able to find it. It's not usually hidden, particularly. So for example, the scientific calculator that comes with Windows, the factorial key on this is N exclamation point. It's right above the 9 key. And so on your calculator, the factorial key may be an exclamation point, or it may be a letter like N or X in front of an exclamation point. I suppose it might even be like FCTRL or something like that, although I can't imagine. I think it's probably an exclamation point. So for example, to find 7 factorial, you type in 7, and then you push the factorial key, and you see that 7 factorial is 5,040. And you can check that. 7 times 6 times 5 times 4 times 3 times 2 times 1 is 5,040. You put a large number in. Actually, now the calculator that comes with Windows actually is pretty good about displaying really large numbers because it's a computer rather than a calculator. And it's a my version, Windows at least, is a 64-bit version. So here we have, for example, 100 factorial is a 9 and some decimals, but it's basically a 9 followed by 157 zeros. That is an incredibly large number. So we can do a 10,000 factorial. We get an error. The error you're going to see on your calculator for this is called an overflow error. How large it is just depends on the type of processor that your calculator has, how much memory your calculator has, things like that. For example, I'll show you the other one I'll show you is the calculator we use in all of our other math classes. Look, statistics. Get rid of statistics for right now. On the TI, 83 and 84, the factorial key is hidden under the math menu and the math button, I should say. So here, if I want to find, let's say I want to find 9 factorial. First, type in the number, and then go to math. Go over to probability, which is sometimes called PRB on older models, and choose option 4, which is an exclamation point. You get 362,000, which is the same as 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Again, if you put in a larger number, however, like 70 factorial, you're going to get an overflow error. How big a number a calculator can handle just depends on the type of calculator. There are ways to work with really large factorials, though, that we'll see in a little bit. So one thing you definitely want to do after class today is you want to be able to find where that key is on your calculator. Now, if you don't have a scientific calculator like is required in this class, then you might not have a factorial key. You just have a calculator that has numbers and the 4 operations on it. That calculator is probably not a scientific calculator. If your calculator doesn't have sine, cosine, and tangent on it, it's not a scientific calculator, and it probably doesn't have a factorial key. In that case, you're going to have to do this by hand or get a better calculator. Any questions so far this afternoon? All right. We're going to, as you're working through the formula for permutations today and later for combinations, probably also today, you're going to deal with some division involving factorials. You don't need your calculator to do this. And in fact, some of the homework problems may even say, oh, don't use your calculator. I'm not going to tell you that you can't use your calculator. I will say for some of the problems, you might not be able to because the numbers are so big. So for example, if we had 8 factorial divided by 5 factorial, we can cancel. We can cancel 5 factorial. This is just 8 times 7 times 6, which is 336. To do this, for your numerator, when you're doing this, your numerator is always going to be larger or equal to your denominator. It will never be smaller because your answer is always going to be an integer. It will never be a fraction. It will never be a decimal. It will never be negative either, for that matter. So your numerator is always going to be larger. If it's not, something's gone horribly wrong. And so what you do is you start with the numerator and you just start writing it out. You stop when you get to the denominator's value. So here we have 8 times 7 times 6. My denominator is 5 factorial. I stop there. And then write it over the denominator, cancel, multiply. This is the same as writing out 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1, and then doing lots of canceling. Same thing, just more convenient, more compact. Similarly, the one underneath it, 26 factorial divided by 21 factorial. Notice what we do. We start with 26 and we start multiplying them out. 26 times 25 times 24 times 23 times 22. And we stop when we get to what the bottom number is, what the denominator is, 21 factorial. We can then cancel, and we just get 26 times 25 times 24 times 23 times 22 equals 7,893,600. This is how you can handle it when your calculator can't handle super large numbers. So for example, I'm going to switch here for a few minutes. Look, statistics. Let's say we had this problem. My calculator cannot handle this. Now, actually, the one built into Windows probably can, but a handheld calculator can't, even a really good one, or at least most really good ones. Let's try it. So 84 factorial divided by 80 factorial gives me overflow error. Oh no, whatever can I do? Well, I can resort to doing this by hand. This is going to be 84 times 83 times 82 times 81 times 80 factorial over 80 factorial. The reason why I can do this, right, is because this would be the same as if I just kept going, times 80 times 79 times 78 times 77 times 76, all the way down to 1. So these cancel. 80 factorial divided by 80 factorial, those common factors divided by themselves are 1. So I get 84 times 83 times 82 times 81. My calculator can handle that. 84 times 83 times 82 times 81. And I get 46,308,024. That's certainly a large number, but it's not too big for the calculator to handle. The calculator can definitely display the answer to this problem. What the calculator can't do is handle those super large numbers of 84 factorial or 80 factorial. But you can still answer that problem. You can still use the calculator to help you, obviously. I'm not going to make you multiply that out by hand. But can't say it one more time.
Can't see your screen. I just see you.
Can other people see the screen?
I can see your screen.
All right, I'm going to try. So TJ, I'm going to unshare and reshare and see if that helps you. Otherwise, you need to log out and log back in.
Okay. There we go.
Okay. Any questions about how to solve division problems like this involving factorials? Again, for small ones, you could definitely use your calculator, but sometimes there's no need to. Sometimes for a small one, like 12 factorial divided by 10 factorial. It's really probably almost faster, or maybe faster, to do it by hand. Especially what 12 times 11 is. That's 132, I think. You can't just cancel the factorial signs, by the way. This isn't the same as 12 tenths. Be aware of that. All right. So let's now look at a formula for permutations. This is a formula that probably should go in your notes, depending on your calculator. Some calculators have built-in functions to handle permutations. If yours does, you do not need to use the formula. You may just use your calculator. If yours does not, you will have to use the formula. Most scientific calculators, although they probably have a factorial, they should have a factorial key. In most cases, they will not necessarily have a way to do permutations built in. Most graphing calculators, on the other hand, will. And certainly some scientific calculators may as well. Just depends. And again, same thing as before. Feel free to take a picture of your calculator, send it to me, and say, hey, I can't find it. Can you help? And I can take a look, do some Googling, and see if I can figure out if yours can handle permutations or not. So the formula is kind of funky looking. And one thing I want to point out is that different books present this part on the left differently. If you take statistics, for example, the way the statistics textbook writes permutations isn't the same as this. The formula is the same. The notation on the left-hand side is different. If you took pre-calculus in high school, you may have done a different way as well. There's at least 3 different ways to write permutations. This is kind of the most common way, though, which is a good thing. So if I have a total of n items, like if I have a total of 20 books to put on the shelf, and I'm going to pick 5 of those 20, how many different ways could I choose 5 out of 20 books to put on the shelf where order matters? So it matters which book I put on first, which book I put on second, which book I put on third. So that would be, so in that case, my total number, n, would equal 20. And the number I'm picking to put on the shelf is 5. And we would write that like this: 20, capital P, 5. The P here isn't a variable or anything. It just stands for permutation. Sometimes people read this 20 pick 5, P for pick. And to find this out, we plug these into this formula. The numerator is 20 factorial. The denominator is in parentheses 20 minus 5, so that's going to be 15. Outside of parentheses, factorial. So this is 20 factorial divided by 15 factorial, which is 20 times 19 times 18 times 17 times 16 times 15 factorial divided by 15 factorial. So we can cancel those 15 factorials and we get 20 times 19 times 18 times 17 times 16. 20 times 19 times 18 times 17 times 16. We have 1,860,480 ways to choose 5 books out of 20 if it matters which book we choose first, second, third, fourth, and fifth. This would be similar to, let's say there was a race. There were 20 runners. The race is part of a series where the winner gets 5 points, second 4 points, third place gets 3 points, second place gets 2 points, fifth place gets 1 point. No one else gets any points. How many different ways are there for 5 runners out of 20 to finish the race in the top 5 positions only? 1, 2, 3, 4, 5. There are 1,860,480 different ways to pick 5 out of 20. If it matters what comes first, second, third, fourth, fifth. Permutations get really big really quickly. In a small situation, they aren't that big. If they were just running and we're interested in who the top 2 runners were, there wouldn't be nearly so many possibilities. But permutations get really large really quickly. For a problem like 20 pick 5, as I mentioned, some calculators have built-in permutation functions, and you can use those if your calculator has one. I'm going to show it to you on the TI-84. Clear is what I want. Go to Math, go to Probability, and choose option 2, NPR. Depending on which version of the TI-84 you have, it might look like this, or the screen might look different. Here, the math print is turned on, which is like the fancy print to make it look more like it looks in math textbooks and stuff. So I would type in my 20, that's my N, and then out of that is my 5. My larger number always goes first, right? I couldn't pick 20 out of 5. That wouldn't make any sense. That would give me an error message. That's impossible. But I definitely could pick 5 out of 20. And that equals 1,860,480. If you have an older TI, like a TI-83 or an original TI-84 Plus, that might look a little bit different. I'm going to turn math print off. Whoops. Math print off here so it looks even more different. So on this older model, instead of PROB, it's just PRB. You still would go to NPR. And here you have to type in the number in front of it. You have to type in the number first, actually. I type in the number first. You have to type in N first. And then go to Math. PRB for probability. Choose NPR. And then pick, or then type rather, your R. So it's a little more clumsy on the older model. On some older models, you can turn math print on. You do that from the mode menu. That might help a little bit. Let's see if I can, nope. I still have to do it that way. So 20, number N first, then PRB, option 2, and then your arm. So I much prefer the model with a little better resolution. Easier on my eyes. So if your calculator, and again, other graphing calculators besides the TI also can handle permutations, and some scientific calculators can as well. If your calculator can deal with permutations, you are free to use your calculator. You do not have to use the formula. If your calculator can't, you will have to use the formula. So, for example, you and 19 of your closest friends have decided to form a business. The group needs to choose 3 officers for the business: a CEO, an operating manager, and a treasurer. You want to know in how many ways could you fill those 3 offices. This is a permutation problem because order matters. It matters who is CEO, who is operating manager, and who is treasurer. So we have our N is our total number. It's 20 because it's you and 19 other people. So N equals 20. And our R equals 3 because we have 3 spots to fill. So this problem is 20P3. So that is 20 factorial divided by 20 minus 3 factorial, which is 20 factorial divided by 17 factorial. That's going to be 20 times 19 times 18 times 17 factorial over 17 factorial. Those 17 factorials cancel. So we have 20 times 19 times 18. I'm going to use my calculator off screen to do that multiplication. 6,840 ways. Again, we want to label. And again, using a calculator becomes much simpler. Math, probability, NPR, P for permutation, 20P3, 6,840. Finally, for permutations, duplicate items. Sometimes you'll have a series of items and something will appear more than once. The most common example used for this type of problem are letters. If this exact same thing is there more than once, how many different ways could we arrange the entire group? I guess we could use books, for example. If I had 3 books, not 3 books, that's not going to work for this, I don't think, very well. If I have 10 books, but 3 of them are the same, like I have 3 copies of the same book, how many different ways could I arrange those 10 books on my bookshelf? That is done using this special formula, and there's not a way to do this on a calculator. You have to do this by hand. N, the numerator, is the same as it is otherwise in a permutation problem, just N factorial, it's the number. So here, let's say I had 10 books. So I have 10 books. Let's say I have more than just, let's say I have, of those 10, 3 of them are the same, and then another 2 of them are the same. Okay, so in my 10-book collection, I have 3 copies of your math textbook, and I have 2 copies of the MLA handbook for reasons. How many different ways could I arrange those 10 books? Well, here's the thing. I don't want to count the books I have multiple copies of more than once. It doesn't matter if I'm putting copy 1 of your math textbook in slot 1 or copy 2 of your math textbook in slot 1. That's going to be the same arrangement. And so that would be 10 factorial, my total number of books, and I divide that by the product of the factorials of my books I have multiple copies of. So this is going to be 10 factorial divided by 3 factorial times 2 factorial. And we can still simplify this the same way. It's a little bit tricky. So 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 factorial. For my denominator, 3 factorial, but then I have to write out any other factorials I have, times 2 times 1. So my 3 factorials cancel, and my 2 is going to cancel. 2 will cancel with 4. So I have 10 times 9 times 8 times 7 times 6 times 5 times 2. That would be 10 times 9 times 8 times 7 times 6 times 5 is 30 times 2. So if I did my multiplication right there, I would have just over 300,000 ways to arrange those 10 books, considering that I have duplicate items within my collection. And so it doesn't matter where I put the duplicates. They're all considered the same book. The most common example for this are letters and words, like Mississippi. Mississippi has repeated letters in it. Our total number of letters in Mississippi is 11. There are 11 letters in Mississippi. So we know we're going to have 11 factorial over something. We have repeated letters in Mississippi, right? We have 4 I's. So that's going to be 4 factorial. We have 4 S's. That too is going to be 4 factorial. We have 2 P's. So that is going to be 2 factorial. And so I have 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 factorial over. So I'll write one of my factorials. I'll keep it as 4 factorial so I can cancel it. My other one I'm going to write out times 4 times 3 times 2 times 1. That's my other 4 factorial. And then my 2 factorial times 2 times 1. So now I can cancel. I'm going to choose a different color, I think. Make it a little bit clearer, maybe. So I can cancel 4 factorial. And then I can do more canceling. All right. 4 times 2 are 8. 3 times 2 are 6. And so I get 11 times 10 times 9 times 7 times 5. Are the things that are left. I only have 1s in my denominator. Remember, my answer for a problem like this is always going to be a whole number. If my answer ends up being a decimal, I say, oh, it's 22.5 different ways. Something went wrong. I canceled wrong. So that's a way to sort of check your work and see, is your answer reasonable? So 11 times 10 is 110, times 9 times 7 is 63, times 5 is 34,650 if I did that multiplication right. Different ways. 34,650 ways. And I did it right, yay. Now, you don't have to cancel at all if you don't want to. In other words, I could just, or you could just cancel the factorial and just multiply 11 times 10 times 9 times 8 times 7 times 6 times 5. and then divided that by 4 times 3 times 2 times 2, you would have gotten the same answer. Canceling just makes it a little bit quicker for when you get your answer, I think. So that's what you do if and only if there are duplicate items. And we're only doing this in this class if we're using all of the items. So all 11 letters in Mississippi, for example. There are ways to sort of combine the formulas. So you could say, okay, how many ways could we, pick 8 of the letters of Mississippi and arrange those, which require us to combine this formula and the permutation formula. And we aren't going to worry about that. So it's a little more in depth. Any questions so far? All right, we're about at a halfway point. Give yourself a little stretch. Take a few seconds to clear your mind. One of the problems with an 85-minute class versus a 55-minute class is that because it's longer, we have to cover more topics. We cover the same total topics throughout the semester, but we have to cover more topics each day because we meet just twice a week rather than 3 times a week. And one of the reasons that gets complicated here is because we're going to do permutations and combinations in the same day. And combinations aren't tricky. Particularly. The problem is permutations and combinations are super similar and people get them confused. So I'm telling you this because I want to make sure that we don't get them confused as much as possible. And so we have just 2 objectives for this part. Objective number 1, we're going to distinguish between permutation and combination problems. And objective number 2, we're going to solve problems using combinations, using the combinations formula, or again, using a calculator if you have a calculator that can handle it. So a combination of items occurs when we take items from the same group. We don't use any item more than once, but order doesn't matter. It doesn't matter what I choose first, second, third, fourth, etc. So this is the big difference. This is the only difference, in fact. For a permutation, order matters. For a combination, order doesn't matter. That is the key difference. Was different too, obviously, but the difference in concept. In a permutation, order matters. It matters who comes in first, second, or third in the race. It matters who is chosen for president, vice president, or treasurer. It matters what order third graders line up in. In a combination, it doesn't matter. Maybe there's an election for student government, and it doesn't matter who gets the most votes, the second most votes, or the third most votes, because the top 3 vote getters are all going to be a student senator. And so it doesn't matter if the order is Teresa, Jeff, Alicia, or Alicia, Jeff, Teresa, or Teresa, Alicia, Jeff. It doesn't matter who comes in first, second, third, because they're all going for the same sorts of positions. If you're packing books to go on vacation. So before we had 20 books and we were picking 5 of them to put on our bookshelf. Now we have 20 books and we're picking 5 to bring with us on vacation. It doesn't matter which book we picked first, second, third, fourth, or fifth. We're just picking them. The order doesn't matter. So for example, we're first going to just do some more examples of distinguishing between the 2. 6 students are running for student government for the positions of president, vice president, and treasurer. The student who gets the greatest number of votes becomes the president. The second highest vote getter becomes the vice president. And the third highest vote getter becomes treasurer. How many different outcomes are possible? Here, order matters. It matters who comes in first, second, third. So this is an example of a permutation. the order matters. Because whether you come in first or second will determine whether you're going to be president or vice president. 6 people are on the board of supervisors for your neighborhood park. A 3-person committee is needed to study the possibility of expanding the park. How many different committees could be formed from the 6 people? In other words, how many different out of 6? Here, it doesn't matter who's picked first, second, or third for the committee. So this is a combination problem. They're not filling different roles. They're all have the same equivalent role. They're committee members. If we are given 4 letters, we could compare how many permutation combinations are possible if we chose 3 letters at a time. So for example, what we see here all together are we have 4 rows and each row has like 6 in it, if I'm doing that right. We have a total of 24 different permutations. There are 24 different ways to arrange those 3 of those 4 letters where the order matters. So ABC is different than ACB. But combinations are different. Every element in this column, for example, has just one combination, ABC. The second column, you can't see my cursor, the second column has the combination ABD. The third column has the combination ACD. And the fourth column has the combination BCD. And so what we see here is the difference between 4P3 and 4C3. And so just using the calculator, 4P3, 24, which we would expect because there's 24 choices shown there. 4C3, and a little preview, wrong file, Carl, wrong icon rather. We do combinations the same sort of way on the calculator. It's right next to the permutation function usually. 4C3 is just 4 because we have 4 columns, column 1, column 2, column 3, column 4. So it can matter a lot whether or not we're concerned with order. That's important because on your final exam, there are 3 very similar problems. I can't remember if they have the same digits in them or not, but they're very, very, very similar. For one of them, you are going to have to find a permutation. For one of them, you're going to have to find combination. And one of them, you're just using the fundamental accounting principle. It doesn't tell you, oh, be sure to use a permutation here. Oh, be sure to use a combination here. You have to figure it out from the context of the problem. And people often will get those wrong. They will just sort of swap between the 3 of them. Check what you're doing. Think, does it make sense? If you have the same numbers involved, like here we have 4P3 and 4C3. If we have the same numbers and we're choosing the same number out of them, the permutation is always going to be larger than the combination. 12P7 is bigger than 12C7. 13P2 is bigger than 13C2. 5P2 is bigger than 5C2. If the numbers are the same, permutations are always going to be larger than combinations. Here's our formula for combinations. It is a more complicated formula. Again, if your calculator can do this, I would strongly recommend use the calculator. Otherwise, you need to use the formula. It's not super more complicated, but it's a little more complicated, and it's super close to the permutation formula, which is kind of unfortunate. There's one more thing added on to the denominator. We multiply the denominator after we do n minus r factorial by r factorial. So let's do my book example. I have 20 books to choose from. I have 20 favorite books. I want to take 5 of them on vacation with me. It doesn't matter what order I choose the 5 in. How many different ways could I choose 5 books out of my 20 if order doesn't matter? That is 20 factorial divided by 20 minus 5 factorial times 5 factorial. So that's going to be 20 factorial over 15 factorial times 5 factorial. So this should be 20 times 19 times 18 times 17 times 16 times 15 factorial over, keep the largest factorial in the denominator as a factorial. I'll make it quicker for you to cancel. 15 factorial times, and now write out 5 factorial. 5 times 4 times 3 times 2 times 1. Now we can do lots of canceling. So 15 factorial cancels with 15 factorial. 5 times 4 are 20. 3 goes in, let's do 3 goes into 18 6 times, because 3 times 6 is 18. Well, let's do it this way. And 2 goes into 6 3 times. So we should have 19 times 3 times 17 times 16. 19 times 3 times 17 times 16. If I did everything right, that should be 15,504 ways that I could pick 5 books out of 20 where order doesn't matter, which honestly seems like a lot to me. So I'm going to double check. First, I'm going to double check that I multiplied that right. And then I'm going to check it using my calculator to see. Yeah, I multiplied it by 20. My bad. That's on Carl. Let's try this again. So what I should be multiplying, this over here, is not 20, because I canceled that. I think I multiplied that by accident. 19 times 3 times 17 times 16. Now I get a different answer. 19 times 3 times 17. Nice. Well, let's check. Maybe I did do it right, or maybe I made a horrible mistake. So we'll check here. 20 books. I'm bringing 5 on vacation. No, my bad. That was right. 15,504. So it's a case where I thought that number was too big. And actually, okay, because 20 pick 5 would have been over 8. That's right. That was way bigger. That's over 1 million, or almost 2 million. So much smaller, even though it's still a large number. So 15,504, and again, our label is going to be ways. How many 3-person committees could be formed from 8 people? So we're selecting 3 people. That means R will equal 3 from 8 people. So N will equal 8. And so our formula, this is going to be a combination because order doesn't matter, because it's committees. Doesn't matter who is selected first, second, or third. So we're going to have 8 factorial over 8 minus 3, that's supposed to be a parentheses, factorial, times 3 factorial. So that's going to be 8 factorial over 5 factorial times 3 factorial. So that's going to be 8 times 7 times 6 times 5 factorial over 5 factorial times 3 times 2 times 1. And so this we can cancel pretty easily here. This isn't bad. 5 factorial, of course, cancels, and then 3 times 2 are 6. So we get 8 times 7 is 56. There are 56 committees that could be formed. And again, we can check this. So this would be 8C3. And it's a little smaller, so it doesn't use up all of our space. So to find 8C3 on a calculator, we would go to combination function, 8, whoops, yeah, I know I put them both in, C3, and we get 56. All right, now we're going to combine. We're going to combine using combinations and the fundamental counting principle. Back in December of 2011, the US Senate, oh, they have so many typos. Consisted of 51 Democrats, 47 Republicans, and 2 independents. How many distinct 5-person committees could be formed if each committee must have on it 3 Democrats and 2 Republicans? This is a committee problem. Committee problems will almost always be combination problems. I say almost always because I guess a problem might say, oh, we're going to have a chair and a co-chair for the committee or something like that. But if it's just committee members or school board members or Senate members of like a student Senate, city council members, anything like that where everyone has the same rank, then order doesn't matter. It doesn't matter who's selected first, second, or third. So here it doesn't matter in what order people are selected. So this is a combination problem, not a permutation problem. So a committee has to have 3 Democrats on it and 2 Republicans on it, based again on these very old numbers. And so we would have, for example, 3 Democrats, that would be 51 C3. And for Republicans, that would be 47 C2. And I'm going to switch screens here because we're going to do a lot of writing here in a second. So I'm going to write that stuff down first of all so I don't forget it and so we can see it. There we go. And let's switch screens. There we go. So let's begin by doing our combination formula here for 51C3. This would equal, so 51 is our n, so that's 51 factorial over 51 minus 3 factorial times 3 factorial. So that's 51 factorial over 48 factorial times 3 factorial. So this looks like it's going to be a big number, but it's really not going to be that bad. I mean, it's not going to be super great, but it's not going to be that bad. So we have 51 times 50 times 49 times 48 factorial over 48 factorial times 3 times 2 times 1. We can do some canceling here. We can do some canceling here. 2 goes into 25, goes into 50 rather, 25 times. 3 goes into 51. Also because 51, 5 plus 1 is 6, and 3 divides 6. So 51 divided by 3 is 17, So 3 goes into 51 17 times. So what we end up with is 17 times 25 times 49. So 17 times 25, times 49, times 49, 20,825. And we'll check our work on the calculator. 51 C3, 20,825. Excellent. So we have 20,825 ways to pick 3 Democrats out of 51. And then we'll do the same thing to pick 2 Republicans out of 47. So we get 47 factorial over 47 minus 2 factorial times 2 factorial. That's going to be, well, we'll do this extra step. 47 factorial over 45 factorial times 2 factorial. That's going to be 47 times 46 times 45 factorial over 45 factorial times 2 times 1. So we can cancel 45 factorials. 2 goes into 46 23 times. And so we get 47 times 23, which is 1,081. So we have 20,825 ways to pick the Democratic members of the committee, and we have 1,081 ways to pick the Republican members of the committees. Now we're going to use the fundamental accounting principle to find the number of committees that can be formed, which is just those 2 numbers multiplied by each other. This number times this number. So we have 20,825 choices for the Democratic parts, and we have 1,081 choices for the Republican parts. We multiply those numbers together. We get 2,825 times 1081. We get 22,511,825 committees could be formed. So you may occasionally have to do some combinations of more than one thing at a time, like we did here. So combinations, order does not matter. Permutations, order definitely matters. Are there any questions about combinations, permutations, or the counting principle from last time? All right. Well, I know we're done a little early, but we did quite a bit. I don't really want to do 3 topics in a day if I can help it. And we're a little bit ahead of the other class still, so we're good. I'm going to put the participation form in chat. Yeah, that's right. If you cannot see that in chat, please send me an email. I'll send it to you after class. Otherwise, if you do have any questions about anything, please send me an email. Let me know what your questions are so I can help. Remember, enrollment, please contact your advisors if you haven't already. If you have questions about math classes, send me an email and I'll do the best. Have a great rest of your day. I will look forward to seeing you back in class on Thursday. Until then, take care, and I'll see you later. Bye for now.